So we're going to talk about gravitational potential energy. We ask the question, what is the work done moving a particle mass m along a path in the gravitational field of m? Right, and so here's, this is the Earth or the Moon or some object, and I'm moving a satellite or a spaceship along here somehow, right? And so it starts at position R1, and I'm going to move it to position R2, and I have to do work to do that. The whole time, the gravity from this object is pulling this way in the direction of F, and so I have to compensate that by doing work by exerting a force in the direction minus F. And so the d work that I do is minus F dot dr, right? And the dr vector is just every little increment along here, right? There's a dr. And so as I move along this path, I have little drs going each way. And so I end up with gmm over r squared. That's the gravitational force at some point. E hat r, it's pointing this way because that's the force that I'm exerting to balance the force of gravity while gravity is pulling it this way. And then the work I do is the dot product of that and the distance I move it. And so if I redraw this guy, so let me do it in green. So let's just look at this little dr here, right? I'm going to draw him like that. That's my dr vector, right? He's got a component that's he's got a component that's this way and that way, right? He's got a component that's this way and this way. The work done along the direction perpendicular to gravity is 0. And so this is the only one that matters, is how far I move it toward or away the Earth while I'm doing work. And so the length of this guy we're going to call dr. And you might think that's the length of this guy, but it's not. It's the radial separation. So we're going to say the dot product of these two is dr. That is, it's the radial distance that I move in the process of moving this little dr vector step. And so what we get is dw is equal to gmm over r squared dr. And then if we want to integrate this from R1 to R2, all the vector stuff has gone away from this. And so if I call the integral of this just w, right, I could, it's just a work done going from 1 to 2. It's just evaluate this at 2 and 1. And so it's minus gmm times 1 over r2 minus 1 over r1. Right. And so we'll talk some more about this in a second. So this is the work that you have to do to move a particle from R1 to R2, and notice that for that integral the result came out as only depending on the endpoints, which makes it a conservative force, which we already knew. But once again, when you integrate the work done, it just depends on the endpoints. The work done by the field is equal to the negative of the potential energy, but this isn't the work done by the field, it's the work done by you, which is equal to the potential energy. And so we can write the potential energy. If this is the change of potential energy, final minus initial, then this is the formula for potential energy. And so there are a couple things we notice. First of all, V of R equals infinity is 0, right? If I stick in a very large R, the potential at 0 is 0 at infinity. So and so you can kind of think something that's in a gravitational field is kind of trapped there. It's got a negative potential energy and it needs to get to 0 to get out. And so anytime an object is gravitationally bound, whether it's the Earth to the Sun or the sun to the center of the galaxy, or the moon to the earth, or us to the earth, we're all of those objects we would say have a negative potential energy, and if you want to get them free, you have to give them enough kinetic energy that they can that'll make their, when added to their potential energy, will give you zero, so they can escape to infinity. So, for example, if we wanted to escape Earth, but just barely escape, we'd say PE final equals KE final equals 0, and that would mean that that as it left the Earth, it would get all the way to zero potential energy, and when it got there, it would have no kinetic energy left, and so it would just barely escape, right? And so if we're starting from the Earth's surface, we would say, PE initial plus KE initial is equal to PE final plus KE final, which is 0, right? And so that means KE initial equals minus PE initial. And so 1/2 m V initial squared is equal to negative of minus G m over the radius of the Earth, right? Because that's where we're starting from, on the surface of the Earth. And so we can cancel the m's, and we get V initial squared is equal to 2g mass of the Earth divided by the radius of the Earth, or the escape velocity is the square root of 2g times the mass of the Earth divided by the radius of the Earth. If we evaluate this, we get about 11 kilometers per second, something like that. So you could do that for leaving the sun or leaving anything. Notice, by the way, that you can kind of see that if you take an object and make it more and more compact, in other words, you keep its mass the same, but you make its radius smaller, the velocity has to increase. This is called the escape velocity, right? So if you took the sun and shrunk it down smaller and smaller and smaller, made it more and more compact, which is what happens to stars at the end of their lives, the velocity to get away gets larger and larger, and this is what sort of defines a black hole. Eventually, if this radius gets small enough, the escape velocity exceeds the speed of light, and that's the thing we call a black hole. So we've already shown that a 1 over r squared force is conservative back in chapter 4, I think, or 2, maybe it's 2. We can show that any isotropic central force, whether it's 1 over r squared or any other, as long as it only depends on r, is conservative. And so it could be a 1 over r squared, 1 over r cubed, or the sum of those, or something like that. And we do this by taking the curl, just like we did the last time, but this time we'll use spherical coordinates. It makes it easy because all of the dependence of the force is in this guy, and it's just that f of r term. These guys are both 0, that is, the force does not have any dependence on theta or phi, because we've said it's isotropic, right? And so you get a 0 here, and a 0 here, and there are only 2 terms left. So, you know, it would be this times that minus that times that. Both of those end up being 0. And it's this, it's minus this times that, which is 0, minus that times that. And so we end up with a comes out as positive, because it's a negative here and a negative on there. And so it's positive. It's a 1 over r squared sine theta for this guy times r e hat theta times df partial f partial phi, and then this guy has a term. It's that times that minus that times that, and so it's it's going to be a minus sign because it's that guy's positive, but that times that minus that times that, so it's negative, and so it's 1 over r squared sine theta for this piece times r sine theta for that guy, e hat phi, times partial lowercase f, partial theta for this guy, right? And we can see this is 0 because partial f partial phi is 0 and partial f partial theta is 0. And so so any central force is conservative.